Okay, let's get started. Welcome, everyone. We'll be talking about more graph theory today, but graph theory also as it relates to the linear algebra that we've been talking about. We'll come back to this problem in a few slides. Course announcements. The problem set, again, problem set 2 is due at 11:59 p.m. Montreal time next Friday, not this Friday. There will be office hours. So first of all, Vincent has office hours as usual tomorrow. My office hours will be moved to 11:30 a.m. Montreal time this Friday. That's because of the iClear conference deadline. So they'll be starting at 11:30 a.m. at the same Zoom link. I will also post in the Slack about that. Are there any questions about the course? Are there large questions? Are we sticking to the original schedule of topics in the syllabus? Roughly. This is still on track for what's been outlined in the syllabus. There may be some small changes. Will PSET 1 be graded before the deadline so we get a feeling of the grading scheme? Yes, I hope so. We can give you an update on that next class. Any more questions? Okay. Let's move forward. So sort of finishing up from last class, but there's going to be a transition from linear algebra back to graph theory because it turns out the two are really closely related. Okay. So let's cast our minds back to eigenvectors and eigenvalues. Let's prove that for any square matrix, eigenvectors with different eigenvalues are linearly independent. Suppose that we have some eigenvectors with different eigenvalues. What can we do? What are some approaches we could use to show this? We want to show that some eigenvectors are linearly independent. So yeah, I like the idea of contradiction. I like the idea of taking a linear combination. Suppose towards contradiction that there is some linear dependence between them. What can we do with that? There's a comment about vectors that normalize the vector. We're trying to prove that these vectors have to be independent. I'm not quite sure if what you're suggesting is a proof, but there may be other ways to go about proving this. So what can we do here? Yeah, we can multiply by A. That's sort of what you do with eigenvectors if you're trying to prove something, because we know eigenvectors have this property where if you multiply them by A, you're basically multiplying them by a scalar. So let's multiply both sides by A. The left-hand side becomes 0. It's just 0 multiplied by A is 0. Then we have all of these. Okay, so that means that we have C1 times A times V1, which becomes C1 lambda 1 V1. And likewise for all of these other vectors. Okay. What now? We have two linear combinations, both of which are equal to 0. Some of the eigenvalues could be 0, or I guess they're different eigenvalues. So one of them could be 0. Eigenvalues can be 0. We could subtract the two equations. We then get another linear combination that is equal to 0. Is there any variation of that we could do? Setting them equal to each other would be the same thing as subtracting them, basically. Yeah, we could multiply one of them by some constant and then subtract them. So if we multiplied by lambda k, the first one by lambda k, then the last term will cancel. All the other terms will get other linear combinations. Okay, so now we have a linear dependence with k minus 1 vectors. What do we do now? Yeah, we could just continue the same process, continue reducing the number of eigenvectors. Or there's a clean way to write the proof. Remember, we saw this extremal principle. We could say, suppose we picked the eigenvectors that were the smallest k to begin with, such that it was a linear dependence. Then, as long as we can reduce k, we can show that there's a smaller linear dependence. Contradiction, we're done. So this is the clean way to write it. The less clean way to write it is just say, keep on doing this and eventually you get one eigenvector, and clearly that is not possible to have a linear dependence with just one eigenvector. But the clean way is to use the extremal principle and say, suppose we picked k minimal at the start. Okay. Now, that was for general matrices, showing that eigenvalues are, showing that eigenvectors are linearly independent. Now, what if the matrix is symmetric? Let's prove that the eigenvectors are actually orthogonal. A symmetric matrix is one where it's just symmetric if you flip it across the diagonal, so A is equal to A transpose. Where did we, good question about the previous proof. Where did we use the fact that the eigenvalues were different? So if the eigenvalues were the same, then these two could have actually been exactly the same linear dependence. It was a very good question. Sorry for not saying that. Suppose that all of them were the same. Then we could actually have had, this would have just canceled out completely. Okay. And we know that if you have that a vector and that a multiple of an eigenvector is also an eigenvector with the same eigenvalue. So what that's just basically saying is you could theoretically write down two different eigenvectors which are just multiples of each other, for example. Does that make sense? So yeah, if all of the lambdas were equal, then this every term here cancels. Okay, let's go back to this. Suppose that the matrix is now symmetric. Show that the eigenvectors with different eigenvalues are actually orthogonal. Suppose we have a couple of eigenvectors with different eigenvalues. Remember, orthogonal means that they are perpendicular. That's just a way to say that in a fancy way. And another way to say the same thing is just that the dot product is 0. And I'm going to write the dot product of two vectors in this way as the matrix product of the row vector of one of them and the column vector of the other one. Because a row vector multiplied by a column vector is just a dot product of those two vectors. So that's just another way of writing it. So we want to show that 0 is equal to this product. Now, let's write down some things that we know because they're both eigenvectors. So since v1 and v2 are eigenvectors, we know that this product, if we multiply by lambda 1, we have, this is a v1 transpose, because that's a v1 is just lambda 1 v1, okay? Times v2. Okay, so what can we do with that? Well, we could just use the transpose to turn this into v1 transpose a transpose, because that's how transposition works with matrix multiplication, times v2. And now here's the cool part. We say, oh, well, because A transpose is equal to A, since A is symmetric, this is equal to this. So we have v1 transpose A v2. And A v2 is something that we can also deal with because v2 is an eigenvector as well. And so now we end up with lambda 2 times v1 transpose v2. We started out with lambda 1 v1 transpose v2, and now we have lambda 2 v1 transpose v2, just because A is symmetric. And now from that, we can just subtract these two sides, and lambda 1 minus lambda 2 times this dot product is equal to 0. And so if the two eigenvalues are different, then the dot product has to be equal to 0. So they're orthogonal. Are there any questions? Now, we're not really going to go into this, but there's this notion of an eigenbasis. You can take, for the situation of a real symmetric matrix, you can take the eigenvectors, the n eigenvectors, as an orthogonal basis. N different vectors that are all pairwise orthogonal. Now, if there are a couple of eigenvectors with the same eigenvalue, then you can there will end up being two perpendicular eigenvectors with that same eigenvalue. So I think that answers the question. If you have a repeat eigenvalue, basically, if you look at the characteristic polynomial and the same eigenvalue turns up twice, then you end up having two orthogonal eigenvectors with that same eigenvalue. If it only turns up once, then you only have one eigenvector with that eigenvalue. And again, the reason why I'm writing this as eigenvectors with different eigenvalues are orthogonal is because there are infinitely many eigenvectors, because any eigenvector multiplied by a constant is also an eigenvector with that same eigenvalue. Question about if the eigenvectors are orthogonal, then is the matrix symmetric? And I think the answer is no. More questions? Okay. If you take the list of eigenvectors and stack them up column-wise, does it form an orthogonal matrix? If you've scaled the eigenvectors appropriately so that they all have norm 1, because remember, an orthogonal matrix has to have all of the columns be normalized so that they're norm 1. Yes, there is a standard way to show that an eigenvector is unique. You just normalize it so that it has length 1. Unit eigenvector. The unit eigenvectors of a real symmetric matrix are orthogonal. Okay, let's move on. So, another fact about real symmetric matrices. Prove that if a matrix is symmetric, then all its eigenvalues are real. So remember that eigenvalues are roots of the characteristic polynomial. And in general, a real polynomial could have complex roots. So we need to basically show that if you have an eigenvector eigenvalue pair, then the eigenvalue has to be real in the case of the matrix being symmetric. Now, to do that, we're going to have to look at this notion of a complex conjugate. A complex conjugate is just, if you have a complex number a plus bi, then the conjugate is just a minus bi. And remember, if you recall, we had that if a complex number is a root of a real polynomial, then its conjugate is also a root of that polynomial. So that basically means that if we had an eigenvalue lambda, then we're also going to have the eigenvalue lambda conjugate, lambda bar. We can show using this fact that actually, what is the corresponding eigenvector to lambda bar? Well, that's v bar. It's the conjugate of v. It's pretty easy to show that. So you start out with v lambda. You're also going to have another eigenvector eigenvalue pair, v bar lambda bar. Okay, let's see what we can do with that. Remember that from the previous result, we knew that any two eigenvectors with different eigenvalues are going to be orthogonal in a real symmetric matrix. So that means that v bar and v are orthogonal in complex number space, complex vectors, if lambda bar is not equal to lambda. So if these two eigenvalues are different, then the corresponding eigenvectors have to be orthogonal. Is this possible? Can a vector and its complex conjugate be orthogonal? No, it can't be. And that's because if we take the dot product of a complex vector with its conjugate, we're going to end up with some things that look like this. The product of a complex number and its conjugate. And the product of a complex number and its conjugate, even though we didn't talk about norms of complex numbers, but if you multiply a complex number and its conjugate, a plus bi times a minus bi, you get a squared plus b squared. And that's just by canceling these things out and by using the fact that I squared is equal to -1. I have a squared minus ab plus minus abi plus abi minus b squared I squared. And minus b squared I squared is just equal to plus b squared. So because of that, we have that the product of any two of a complex number and its conjugate is always non-negative because the sum of two squares of real numbers is always non-negative. That means that we can only have v bar dot v equal to 0 if v is itself 0 and no eigenvector is 0 by definition. So that means that if you have v and v bar being eigenvectors, then they have to come with the same eigenvalue from the previous result. Because they had different eigenvalues, they would be orthogonal. Now, when is lambda bar equal to lambda? That is the case when lambda is actually a real number. The only case when you have a plus bi is equal to a minus bi is if b is equal to 0. So that shows that there can actually be no eigenvalues except for real eigenvalues if the matrix is symmetric. Other questions about this? Okay. So, a little bit more linear algebra before we get to why it's important for graph theory. First, powers of a matrix. We can write the power, the kth power of a matrix, a to the k. It's just it's notation for a multiplied by itself k times. It's just as if we're writing the power of a variable. So a squared is just a times a cubed is just a times a times a. Now suppose that A is an n by n matrix with all different eigenvalues. What is a to the k times v for general vector v as k gets really large? What do you think about that? So, to start us off, we know that A has n different linearly independent eigenvectors with some eigenvalues, because these are all different eigenvalues. Okay. Now, what happens with powers of A? So A times any one of these eigenvectors is going to be a multiple of that eigenvector just because it's an eigenvector, by definition. So A squared is also going to be a multiple of that eigenvector. If we just square the eigenvalue, we get the corresponding constant. A cubed is also going to have this property. So what we have is that each eigenvector, Vj, has to be an eigenvector of a to the k for every k. And the corresponding eigenvalues just also take kth powers. So if you started out with eigenvalue 2, then you get eigenvalue 4, and then eigenvalue 8, and then eigenvalue 16, and so on. Because you're just multiplying by a that number of times. Okay. So suppose that we have this vector v. Now, since we have these n linearly independent eigenvectors, we can write v as some combination of those eigenvectors. Now what can we do? Yeah, we're going to want to apply a to both sides of the equation because we're looking at a to the kv, right? So what happens if we do a to the kv? A to the kv is going to be equal to this other linear combination of the eigenvectors. And the cool thing is that the eigenvectors are eigenvectors of a to the k with eigenvalues lambda 1 to the k, lambda 2 to the k, and so on. So just by multiplying by a to the k, we get another combination of the same eigenvectors. So as k gets really large, what happens? Yeah, the result gets either gets really big or really small. But indeed, there's going to be one term which is going to dominate, the one where the absolute value of lambda is the largest. That one is going to blow up much more than the others. And we'll see that also when we get to calculus. But if you take powers of something large, it gets larger disproportionately fast. So as you have a k going to infinity, we're going to approach a multiple of the top eigenvector, the one where the absolute value is the largest. And this is the case even if the eigenvalues are smaller than 1, it's still going to be a multiple. The multiple is just going to be getting smaller and smaller and smaller. But still it will be larger than all of the other eigenvectors. Basically, one of the eigenvectors will be growing much faster than all the others. I didn't really consider the case where you have complex eigenvalues here. Maybe I should have said if A is symmetric. Technically, if you have complex eigenvalues, this is going to hold 2. It's just you will have 2 conjugate eigenvalues which have the same norm and both get large together. So you're going to have 2 eigenvectors that get large together, conjugate eigenvectors. Does it matter which C is the largest 2? So the C is not changing with K. Basically, the point is just that no matter which vector you start with, if you multiply by a matrix enough, it's always going to be pointing in the same direction. Does that make sense? So if you just keep on iterating this matrix, you end up sort of always going in the direction of one vector. That vector is going to be really long, but it's always going to point in that direction. We'll see how this is relevant in a few slides. Okay, so now this is probably the thorniest part of the whole class. So if you didn't get all of that, this is a good moment to dial back in. We're about to switch to graph theory, but also first, just a quick application of eigenvectors and eigenvalues, principal component analysis. Sometimes, this is just to see an application, sometimes it's very high dimensional data and we'd like to approximate it using a lower number of dimensions. This is, for example, for visualizing it, or if we want to just understand some important features about that data. So principal component analysis is one very simple way to do this. Suppose we have some data points, we have m different data points, and each of them is a vector in r to the n. We can represent this data as a matrix. A matrix X in r to the n cross n. And then we can look at the covariance matrix, which is the I'm sorry, I realize there's a typo in a moment in this slide. So I'm actually going to skip over the rest of this slide. Sorry about that. Just, I realized it would be a little bit confusing. It's not going to be necessary to discuss PCA here. Sorry about that. Let's go to the graph theory applications right now. So the The graph theory applications that of all the linear algebra that we've been doing. Let's start out with why graphs are related to matrices in the first place. Yes, sorry. So let me just say in words what's going on with PCA. So in PCA, you can represent the data as a matrix, an n by n matrix. And you look at the covariance matrix, which represents basically pairwise similarities in the data. That's just X transpose times X. I think the issue is like with the transposes here. Sorry about that. So you're looking at how similar different data points are with each other. And then what you're basically doing is you're doing you're decomposing that into eigenvectors and looking at the how to represent individual data points in the basis of eigenvectors. And so what you end up, no, I think, is this all correct? I think so. Sorry. Yeah, so you have these various eigenvectors, and these are, yeah. So since it's sorry, and I think everything's good. So since this matrix is symmetric, it has all real eigenvalues, and the eigenvectors of the matrix are going to be all. So we didn't talk about what happens if two eigenvalues are the same, but you can, as I mentioned, you can always have n different pairwise orthogonal eigenvectors. So these are called principal components, and these are just a new basis, basically. And so you can express each data point in R to the n in terms of this basis. And the idea is that these capture the directions which are varying the most across different data points. So since because they are the eigenvectors of this matrix, they are the dimensions across which the data varies the most. And so you can see that in this picture, for example, if you have this sort of scatter plot of lots of data, and you can imagine this being high dimensional, if you look at the covariance matrix of this data and you pick out the eigenvectors, the eigenvector with the greatest eigenvalue is going to point in this direction. The eigenvector with the second greatest eigenvalue is going to point in this direction. And you can basically say that the top eigenvector is the direction where the data is varying the most. The second, the eigenvector with the second largest eigenvalue is the direction in which the data is varying the next most, and so on. And so if you wanted to represent 100-dimensional data, you can use the top eigenvector followed by the next top eigenvector and represent that in as a 2-dimensional plot. Hopefully that helps a bit. Sorry, I realize I should have gone into more detail on this, but I would like to move on to graph theory because there's a lot to cover today. Okay, so let's go to the adjacency matrix. Suppose that we have a graph with n vertices. The adjacency matrix is another way to write the graph. It is another description of a graph. So it's an n by n matrix where you have a 1 in an entry if 1 in an entry ij, if ij is an edge, and 0 otherwise. So as an example, here is a 5-vertex graph. A, B, I've labeled the rows and the columns A through E. So for example, the entry in A, row A, column B is 1 because there's an edge A to B. There isn't anything in AC because there's no edge from A to C, and so on. This is always symmetric, and that's because AB is the same as BA in the case of undirected graphs. We'll see what a directed graph is in a moment. There's always a symmetric matrix. What happens if we sum all the rows in the adjacency matrix? We're going to get the degree of every node. So if we sum up all of the entries, all of the rows, we're going to get, in column A, we're going to get the number of things that are connected to A. So 1 for B and 1 for D, because A is connected to B and D. So we get the degree of A. Then we get the degree of B, which is 3, and the degree of C, which is 2, and so on. Great. Same if we sum up all the columns, because this is a symmetric matrix. Okay. Now let's look at directed graphs. In directed graphs, you can think of each edge having an orientation. You can also think of it as being an ordered pair. I realize we're not really going to talk about directed graphs very much in this class. Maybe in future lectures, not sure. I wanted to give an idea of how this carries over into the adjacency matrix. So this is one way that people represent directed graphs. Generally, they put a little arrow at the end of each edge to indicate which way it's pointing. So this is the edge 1, 2. This is the edge 3, 2, and so on. Notice that you can have two edges between the same two vertices going both directions. So this is 3 to 4, and this is 4, 3. Okay. Some examples of why you might use directed graphs. In social networks, for example, if like friending someone is not symmetric, or movement between places, like indicating that there is movement, there's flow going from this place to this place, and it's directed. Dependency relationships, or things like predator-prey relationships and so on. Directed graphs are important. So what happens to the adjacency matrix? Well, it's no longer symmetric. If there is an edge, and this is the adjacency matrix of this graph, so there's an edge from 1 to 2. So in row 1, column 2, there's a 1. Similarly, there's an edge from 3 to 4. So in row 3, column 4, there's a 1. But there's also one from 4 to 3. So here there is a 1 as well. But yeah, in general, it's no longer symmetric because an edge from A to B doesn't mean there's an edge from B to A. Let's take a look at another variation on graphs, which also affects the adjacency matrix. In weighted graphs, each edge has a weight associated to it. And this comes up in lots of different applications. For example, the lengths of roads, or time to travel along the road, resistances in wires. If you have pairwise similarities, if you're trying to use a graph to represent similarities between different objects, and the vertices are your objects, and the edges are the strengths of the similarities between them. Those are some situations where this comes up. And we'll see this later in terms of max flow. So what happens to the adjacency matrix here? Well, instead of having ones where two things are adjacent, where two vertices are adjacent, we have weighted entries. So for example, A to C, this is row A, column C, is 5. You can, it's a bit like if you just had 5 different edges between A and C. Okay, so now we've seen this. Let's take a look at random walks. And this is where the matrix representation of a graph really ties in with the linear algebra. So often graphs represent a flow of information or objects in a network. Why is the adjacency matrix relevant? Let's look at the square of it. This is the adjacency matrix for this graph. If we square the adjacency matrix, we can look at each of these entries. So for example, this is row B, column E. How did we get a 2 here? Well, what we did was we took the column E of this matrix and we multiplied it by row B of this matrix. And where we have, why we get a 2 is because this dot product is equal to 2. And the dot product is equal to 2 because there's an edge from B to C, and then there's an edge from C, sorry, Yes, and then there's an edge from C to E. Edge from B to C, because this is in row B, column C. Edge from C to E, because this is in row C, column E. And so these two overlap and contribute to the dot product because B to C and C to E is a path. Likewise, B to D and D to E is also a path. And so in general, what you can see is that row B, column E represents the number of ways to get from B to E in 2 steps. Here it was in the adjacency matrix, it's the number of ways to get from B to E in 1 step. In the square of the adjacency matrix, it's the number of ways to get there in 2 steps. Likewise, this is 3 here, because there are 3 ways to get from B to another vertex and then back to B. And that's just because the degree of B is 3. So BA, B, BDB, and BCB are all 2 edge paths. In general, the entry in row I, column J, is just the number of 2 edge paths between I and J. And you can imagine generalizing this as well. If you multiplied by the adjacency matrix again, this is the number of ways to get from B to E in 2 steps. If you multiplied by the adjacency matrix again, you would be looking at the number of ways to get from B to E in 3 steps, and so on. So let's go back to that initial problem for those who started class a little bit early. In the following graph, I start at vertex A and move from where I am to an adjacent vertex each move. What's the probability of being back at A after 10 moves? Well, we see that what we can do now is look at the adjacency matrix and just take the 10th power of it. Now, that's not something I would like to do by hand. I, in fact, use Python for this. But if you were to do it by hand, you could do it pretty fast by just calculating a squared, then squaring that to get a to the 4th, a to the 8th, and just use a to the 10th is equal to a squared times a to the 8th. So you could actually do this by hand if you wanted. Certainly way easier than trying to count all the paths by hand, because there are a lot of them. And now what's the final probability? Well, this is the number of ways to get from A back to A in 10 steps. This is the number of ways to get from A to B in 10 steps. This is the number of ways to get from A to C in 10 steps, and so on. So, since we're starting at A, we know we want to get from A to either A, B, C, D, or E. And so the answer is just the number of ways to get from A back to A divided by the number of ways to get from A to A, B, C, D, E. If you calculate that, it's 0.215-ish. And so now here's the really cool thing. We looked at just the first column of, or alternatively first, the row of A to the 10th. And the different entries gave the relative likelihood of being at different vertices after 10 steps if we started at the first vertex. What happens if we take a really large number of random steps on a connected graph starting at vertex 1? Like way larger than 10. So let's look at a to the k for k going to infinity. The first column of a to the k is just a to the k times this particular vector, 1 followed by all zeros. We know that a to the k v is going to approach some multiple of v, where v is the eigenvector with the highest eigenvalue. And if you were worried before about eigenvalues being possibly complex, you don't have to worry about that, because A is a symmetric matrix and it doesn't have any complex eigenvalues. So, a long random walk on the graph is going to approach a limiting distribution among the vertices, which is just the top eigenvector. It's going to be, so a to the k v1 is going to be some very large, probably, multiple of the top eigenvector. But if you look at just the probability distribution, it's going to be the ratio of all the elements in the top eigenvector. So if you just wander around a graph, and graphs can represent basically any random walk pattern, you're going to eventually end up with a limiting distribution, which is just the top eigenvector for that graph, for the adjacency matrix. Okay. So some other things that are related to the adjacency matrix. First, the diameter of a graph. The distance between any two vertices in the graph is defined to be the length of the shortest path between them. So for example, the distance between A and E here is 2, because the shortest path between A and E is length 2. For example, this is a path of length 2 between them. You could also take a path of length 3, but that's not the shortest path. The diameter of a graph is the maximum distance between any two vertices. So which are the two vertices that are furthest apart? That's the diameter. So as an example of this, there's this famous notion of 6 degrees of separation, that everyone in the world is separated from anybody else in the world by at most 6 other people. And you're like friends with you're like friends with somebody and they're friends with somebody else, and you can get from anywhere in the world to anywhere else in the world. This is just saying that the diameter of in this case, symmetric friend network is 6. Now, it's not probably the case with Facebook, for example, but it is certainly the case that social networks have a pretty low diameter. Or, yeah, 6 degrees of Kevin Bacon, or Erdős numbers, or anything else. These are often called small world networks, where you have this property that the diameter is actually really small. There are other properties for a small world. So diameter, I'm not sure how it will be defined for a weighted graph. Good question. Okay, so how does this relate to the adjacency matrix? Well, it's just the lowest k, such that the kth power of the adjacency matrix has all non-zero entries. Because if you have the kth power having all non-zero entries, then that means that there is a k edge path from any vertex to any other vertex. So I guess that's one way to work out the diameter if you want. It's also just like a connection between things, and I like these connections between them. Okay, and now we're going to finish by looking quickly at the Laplacian matrix. And this is a really, really beautiful and complex mathematical object that I'm not going to do justice to at all. We might look at it a bit later on when we do max flow min cut, but not sure. So the Laplacian matrix of a graph is defined as D minus A, where A is just the adjacency matrix, which we've seen, and D is the diagonal matrix of vertex degrees. So that's just if you take the degree of each vertex and you put it along the diagonal. So here's an example. You're going to see for an unweighted graph, you're going to see a lot of negative ones, and then all these things along the diagonal. So for example, A has degree 3, excuse me. So there's a 3 here, and then there are the 3 edges coming away from it. B, C, and D. COM B, C, and COM D. Okay. And it's going to be symmetric because both D and A are symmetric. D is just diagonal, and A is clearly is symmetric. Okay. What is one eigenvector of the Laplacian? Is there anything that you see that might be an eigenvector? What happens, for example, if you sum up all the columns? If you sum up all the columns, there's 0. Because there are always 3 negative 1s here and 1 3. Or 2 negative 1s here and 1 2, because the degree is just the number of things that are negative 1 in that row. So, since the sum of each row or the sum of each column is 0, then 1, 1, 1, 1, 1, 1, 1 is an eigenvector with eigenvalue 0. Because if you multiply that vector by this matrix, you just get the sum of the columns. Okay. So we have an eigenvector with eigenvalue 0. We hadn't seen that before. It's cool. Notice that it's perfectly allowed to have an eigenvector with eigenvalue 0. You're just not allowed to have an eigenvector that's 0, because that's silly. Just having an eigenvector, having a vector that's 0, it's obviously going to be, if you multiply that by anything, it's going to be equal to 0. But having an eigenvalue that's 0 is totally fine. What if the graph is disconnected? So here the Laplacian is this. Do you see any other eigenvectors here? If you multiply up all the, if you sum up all the columns or all the rows, you're going to still get 0. But what else can you do? I'm sorry, this should be 1, 1 along the diagonal here, not 2, 2. Yeah, sorry about that. I really don't like writing matrices in LaTeX. There are too many matrices in LaTeX to write here. Okay, so we're thinking about doing something different for this block and this block. Yeah, if we had 1, 1, 1, 0, 0, or 0, 0, 0, 1, 1, both of those would end up giving you 0, because it's just the sum of these 3 columns, or the sum of these 2 columns. Both of them would give you 0, so both of them are eigenvectors with eigenvalue 0. Now, here's a subtle point. All 3 of them are eigenvectors with eigenvalue 0, but really there should only be 2 that count here. That's because this one of all ones is actually the sum of the other 2. So there are only 2 orthogonal eigenvectors with eigenvalue 0. That's 1, 1, 1, 0, 0, and 0, 0, 0, 1, 1. If you dot them with each other, you see that that equals 0. So these are orthogonal eigenvectors. And in general, you're going to have one eigenvector with eigenvalue 0 for each connected component of the graph. So if the entire graph is connected, this is just all ones. That's your eigenvector. If there are 2 components, then you have 1, 1, 1, 0, 0, and 0, 0, 0, 1, 1, for example. And those are the 2 connected components. And so this is a really great way to find the components of the connected components of your graph. If you don't really need a special algorithm for it. You just write down the Laplacian, you compute the eigenvectors, and then you can pick out exactly what your connected components are. Okay. Now, on the last slide, let's see why this is really useful. So we won't prove it, but all the eigenvalues here are positive, are non-negative. The matrix is called positive semi-definite because it has all non-negative eigenvalues. And so the eigenvalue 0 is actually the smallest eigenvalue. This is connected to what you have to prove on the problem set. So the reason why this is useful is how might you divide a connected graph in two? Clustering into two separate components of the graph so that they are basically disconnected. Well, suppose the graph is almost disconnected. Then there's a vector of all one, an eigenvector of all ones, and no other eigenvectors with eigenvalue 0, but there is an eigenvector that's really close to all ones and all zeros for the almost disconnected components. And I'm not going to go into formalizing this, but there is a way to formalize it. So what we can do is we can take the eigenvector with the second smallest eigenvalue. It's going to have an eigenvalue that's very close to 0. And we can just compute the sign. We can say which elements of this eigenvector are close to 1, which ones are close to 0. And the best way to do this, turns out, is with the sign. The ones which are positive, we take as +1. And the ones which are negative, we take as -1. Those entries with +1, we put in component 1. And those with -1, we put in component 2. And this is an example of a spectral clustering. We have a graph like this, and we're trying to work out basically a bottleneck in it. We can do that by looking at the second smallest eigenvalue and the corresponding eigenvector and working out which of the components the individual vertices should go into. The way to formalize this is to look at this quadratic form, but we're already over time, so I will not go into that. Thank you all for coming, and I will see you at office hours again at 11:30. Office hours is a little bit later this Friday, 11:30 a.m. Eastern time. And next time we will be having our first class on calculus. Happy to stick around and answer some more questions. Oh, and I will also again do a quick poll about what the speed of this class was. What does the eigenvalue and eigenvector represent in an adjacency matrix? So I am not an expert on spectral graph theory. There are things that one can do with that. For example, if the graph is regular, then the all ones vector is an eigenvector.